Well, welcome back, statistics scholars, and we are moving on to our next topic, a topic called distributions. And the purpose of this lecture is to sort of wrap our head around the ways in which we can visually summarize our data and really ask this question: where are the people? And for the purposes of today's discussion, we're really going to focus only on quantitative data, quantitative variables, where when we're considering one variable, which remember is like a question, researchers are going to ask somebody a question. For example, how many cups of coffee do you drink? And that is a quantitative variable, which is going to generate quantitative data, where people are going to give you answers. Some people are going to say 0. Some people are going to say 1 cup. Other people are going to say 2 cups or 3 cups or 4 cups or 5 cups or however many. Or you might measure it in ounces. And somebody would say, I have 12 ounces. Somebody else may say, I have 16 ounces or 24 ounces. However you decide to measure it, people are going to give you a quantitative answer, a number answer to your question. How many ounces of caffeine do you drink, or how many ounces of caffeinated beverage, how many cups of coffee, however you want to answer it, ask it. And so today we're going to talk about the idea that different variables have different what are called distributions. And what that word means, distributions, when you talk about quantitative data, is that there is a range of possible answers to any question you ask someone. But then there can be patterns of how people answer that question, where you say, well, where are most of the people? And so, for example, let's say the answer to my question, let's say my question again is, how many cups of caffeinated beverage do you drink in a day? How many different caffeinated beverages? And some people say 0 and 1 and 2. Well, I may notice that most of the people are telling me 2. And some people tell me 3, and even fewer people tell me 4, and hardly anybody tells me 0. I may notice that there's some pattern in how people are answering this question, where most of the people are, let's say, in sort of the center of the range. That's one pattern of distribution, because we're asking, how are people distributed? Like you're handing out cups, you're distributing the cups, right? How are people distributed among all the possible answers? And when you ask how many different caffeinated beverages did you have today, possible answers are 0, 1, 2, 3, 4, all the way up to like the person who's crazy and drinks 16 Red Bulls and is about to go into cardiac arrest, right? But there may be a pattern to how people are answering the question, or most of the people are answering the question in a particular way, or there's some pattern that you can see. And we call that idea, how is the variable distributed? Where are the people? Are all the people in the center? Are all the people in the top of the range? Are all the people in the bottom of the range? These are what are called patterns of distributions. And that is what we're going to be talking about today. Distributions when dealing with quantitative variables, quantitative data. So, to refresh your memory, quantitative variables and quantitative data is going to generate information about people. So imagine you have an Excel file, right? And every single person is a row, right? And along the column, you're typing in people's answers. Answers to the question are always going to be numbers. How many children do you have? How many books do you own? How many pets do you own? On a scale of 1 to 7, how tired are you today, right? Quantitative data about people, imagine a big old column of information, are going to be numbers, right? And when you think about the variable as a whole, and you think about all of the people you're going to ask the question to, if you think about all the people who are going to answer your question, you have people falling on a continuum from less to more, right? That the nature of the variable is from less to more of that psychological construct you're trying to measure, right? Or even that physical idea you're trying to measure. You're measuring something quantitative, where people are different based on amount. So mile times, faster to slower. Reaction times, faster to slower. Number of children, more to less. Life satisfaction, from more to less. That's the idea. So let's use a working example. let's say I'm going to be opening up. Let's say I'm a business person, right? I'm doing business stats. They have a company has hired me to figure out some aspect of, help them with their business. And we're opening up a new sporting goods store. It's a big, let's say it's a big sporting good company, Big Five, or I can't think of any others right now. Let's say Big Five Sporting Goods. They want to open up a new one in Encino. And they're going to stock college apparel. And I want to figure out then, in Encino, how much do people like the Brahmas? Pierce College Brahmas. That's our mascot here at Pierce, in case you didn't know. I'm curious how much people like the Brahmas, from more to less, right? So how might I operationalize this variable becomes the first question, because I got to come up with an operational definition, right? Measurement. That was our discussion from last time. And ask yourself, what would make this quantitative? Or another synonym for quantitative is often measured, right? Where you're measuring a specific amount of something. What makes it quantitative? It's this word, right? How much do people like the Brahmas? And I could measure it from 0 to 10. I could measure it from 1 to 7. But at the end of the day, I want to know how much of Brahma love do they have, right? How much Brahma love do they have? That is my question. And here is how I might operationalize that variable. I may decide to ask 15 people in Encino, because I'm trying to open up my new sporting goods store in Encino. I might ask 50 people living in Encino. That would be my sample, meant to represent my entire population living in Encino, right? I might ask them on a scale of 1 to 10, how much do they like the Pierce College Brahmas? First person tells me 7, second person tells me 6, and so on and so on and so forth. And you can see how each person is giving me an answer to a quantitative variable question. And so the data that they're giving me is quantitative, right? Person 1, their outcome is 7. On the variable, how much do you love the Pierce College Brahmas? So let's use a different example. Let's say I have a different quantitative variable. I'm on the city council. I want to try to figure out how fast police officers respond to threat. I'm doing a study to sort of see what is the reaction times of police officers, because I think that reaction times less than 5 seconds are the best. There's actually an optimal range. It needs to be less than 5 seconds, but let's say greater than 2 seconds, because less than 2 seconds is too fast. So no more than 5 seconds, but no less than 2 seconds, right? And so I'm trying to figure out sort of the optimal range, right? So are my officers' reaction times optimal or fast enough, right? How might I operationalize this variable? And again, what makes this quantitative? Well, the fact that I'm going to be probably timing them, right? I'm going to be timing them with a stopwatch, right? And because how I'm going to get at their reaction times is going to generate a number, well, then my data is quantitative, right? First officer 2.11, he has an ideal reaction time, just over 2 seconds, but nowhere near 5. Reaction time of officer number 2, well, maybe that's a little too fast. Maybe he's not pausing long enough to really assess the threat, right? Officer 3, 1.85, Officer 4, 1.91. And I noticed that all the officers' reaction times are around 2. And so maybe that really does seem to be, I have optimal reaction times. Maybe some of the officers are a little too fast, not thinking carefully enough, but right around the right reaction time for many of the officers. Make sense? Right. That's how I'm operationalizing the variable. I'm going to take them to a shooting range and give them various pretend threats, kind of like if you've ever watched Men in Black, the first one. It's from, kind of a while ago, right? But whatever, I remember it. And Will Smith is like, assessing threats along with all the other candidates for Men in Black. That's how I imagine you would operationalize this variable, by simply timing how long they take. So how does this idea relate to distributions? Well, the idea here is that there's going to be a shape to the distribution. And what that means is that there's going to usually be some pattern with how people's scores are falling out within the range on your quantitative variable. People are relatively predictable. People are not random beings. The same kind of factors in the world affect people in somewhat similar ways. And so people are usually a whole lot more similar to each other than they are different. And so there are some very typical patterns with how people are distributed, how people's actual scores are coming out along the various possible outcomes on a particular variable. So if you think about, let's say the range of reaction times was 1.1 second all the way to 3 seconds. People are probably going to cluster together in some predictable way. And that is what we mean by the shape of the distribution. Because I'm actually going to show you some ways to visually summarize this idea of where are the people? How are people distributed? How are people's actual scores coming out? How are they distributed among the various possible outcomes on your variable of interest? And there are some common ways. We're going to learn about normal distributions, uniform distributions, bimodal distributions, and skewed distributions, because these are some really common patterns for people's score to come out. These are really some common ways to answer the question, where are the people? Right? So I'm going to teach you some ways that we can visually summarize, or in other ways summarize, quantitative information to get a sense of the shape. Or asking the question, how are the people distributed? How are the scores distributed? Where are the people? Are the people high mostly? Are people low mostly? Are people in the middle mostly? Are people all spread out? That's the idea. And we call this concept the shape of the distribution. So the ones we're going to go over today are frequency tables, which are useful for some type of quantitative data. Now again, our discussion today about the shape of distributions is really only relevant for quantitative data. It's not relevant for qualitative or categorical data. There are different kinds of summarizations for that kind of data. But if you have a dimension-based variable, so dimension-based data with high scores on one end and low scores on the other, then you can use the techniques we're going to talk about now. So the first way is called like a set of frequency table, and it's useful for certain kinds of data, and it has some pros and some cons. Essentially, the nice thing about a frequency table is that if you can use it, it allows you to identify what are called percentiles. Now, if you took any standardized testing here in California, or if you've ever taken the ACT or the SAT, you might have been told your percentile, where you are in the distribution. They may have said your 35th percentile or 67th percentile, which means your score, if you're 67th percentile, your score on that test was better than 67% of all the other folks. And frequency tables are very good for identifying the scores that are at various percentiles. That's sort of the pro. The con of a frequency table is that it's really only good with discrete data. Remember our discussion of discrete versus continuous? Well, frequency tables are not really appropriate for truly continuous data, but rather only really appropriate for discrete data over a very narrow or limited range. And we'll actually look at some reasons why that is. Histograms are, I think, some of the gold standard of visual representation. Histograms are great. They allow you to quickly visually summarize the literal shape of your data. You can look at a picture to see where the people are, to get a sense of the pattern of your data. Where you group people, you group ranges of scores. You group people's scores who are next to each other together, and then you make a graph. And instead of describing the graph, I'll just wait to show you a picture. But it's essentially you group people's scores and you draw rectangles to denote how many people were in that range. And then you put those rectangles, those bars, along a number line, and you end up with a pretty picture. We're also going to learn about density plots. And density plots are like a smooth version of a histogram. And the word density is actually a mathematical phrase to mean how much stuff there is. A density plot allows us to track how probable or how often a particular score occurred. Density is another word for how much or how probable was this particular outcome. How many people fell into this category? How many people fell into this range of scores? And then a computer algorithm smooths out the histogram and makes it like a nice smooth picture. But again, a picture's worth 1,000 words. So let's look at some pictures. This is an example of a frequency table. And so let me walk you through how to interpret this frequency table. So I'm going to get my stylus here. All right. So along the left-hand side of a frequency table, you have all of the possible choices. All of the possible choices on your variable of interest. And so as you recall, I said that Brahma love was going to be measured on a scale of 1 to 10 from that example from before. Some people were going to say 1, some people were going to say 2, some people were going to say 3, all the way to 10. And so you essentially list all the possible outcomes over here along the left-hand side of your graph. That is how that works. Make sense? So these are your possible outcomes. On the right-hand side, over here, is along this column here that has F at the top. This is going to be how frequently the actual score occurred. So if you look at this frequency table, what you can see is the score of 1. For you to say, on a scale of 1 to 10, how do I feel about the Brahmas? I'll give that a 1. Only one person gave that score. This person. This person right here. The score of 2. 2 people gave that score. 4 people chose 3. 5 people chose 4. 4 people chose 5. 5 people chose 6. 8 people chose 7. 5 people chose 8. 9 people chose 9. And 7 people chose 10. And it's useful as long as you have like a limited number of possible choices. You only have 10 choices here, and so you can sort of get a sense of the pattern using this frequency table, right? You can sort of see that there are more people choosing 7, 9, and 10, 8 people choosing 7, 9 people choosing 9, 7 people choosing 10, then there are people choosing the lower scores. You can sort of see that people are clustering in the upper ranges of this distribution. And as long as you have a very limited range of discrete data, discrete quantitative data, a frequency table can be useful. This is called a cumulative frequency table. And in a cumulative frequency table, it not only gives you the information from the previous slide, it also keeps a running count. So you still have the number of options over here. This is still your possible choices over here on the left. Over here on the right, there's still going to be your how frequently that particular score occurred, right? Where 7 people chose 10. Oh, on a scale of 1 to 10, how do I feel about the Brahmas? 10. 7 people chose that. But then in this last column, you're going to keep a running total as you go. So here, one person chose 1. 2 people chose 2. So 1 plus 2 is 3. So what this is telling me right here is that 3 people chose 2 or below. And so let's zoom down to 6. This is the choice 6. On a scale of 1 to 10, how do you feel about the promise? I choose 6. And I see that 5 people chose 6. 21 people chose either 1, 2, 3, 1, 2, 3, 4, 5, or 6. Because 1 plus 2 plus 4 plus 5 plus 4 plus 5 is, you guessed it, it's 21. You're keeping a running total in a cumulative frequency table. You're counting up as you go, the people as they accumulate as you go up your quantitative scale. It's called a cumulative frequency table. And it is also often very useful for identifying breakpoints, right? You can often say, okay, I noticed that between the scores 6 and 7, I jumped from 21 people to 29 people. So there appears to be, again, more people in these upper ranges of the distribution, because I don't reach half of the folks until I get to 7, a score of 7. It allows you to identify these sort of breaking points. The last kind of frequency table I want to share with you is called a combined relative frequency table. And instead of keeping a running total of the actual number of people in the last column, instead of having like a running total like the cumulative frequency table does, in this last column, you keep track of the proportion or probability at that particular score. This is still going to be the actual choices on the variable. This column is still going to be the number of people that fell into that choice. But then this last column here keeps track of the running total of proportion or probability. And this is actually how a frequency table can help you identify percentile ranks, where at a particular score, a certain percentile, a certain percentage of people falls below that score. And so let's take a look at the 2 examples I have here. I'm able to identify the choice of 3, the score of 3, as the 14th percentile, because a proportion of 0.14 falls below, at 3 or below. And how did we figure this out? Well, I'm not going to ever on a test ask you to create a frequency table, right? I'm only ever going to ask you to interpret frequency tables. That's just my preference, because frequency tables are often generated very automatically, and I think it's much more useful for you to know how to interpret them. But let's go back to the previous slide and see where these numbers came from using the example of 3. So if we go back to this slide, we see if you have the score of 3 here, whoops. You have the score of 3 here, and you see 4 people chose 3, 2 people chose 2, and 1 person chose 1. And so there were 7 people who chose either 3, 2, or 1. Well, if we take 7 and we divide it by the total number of people, that would give us the proportion of people who chose 3 or below. Moving forward to this slide, 7 divided by 50 is, you guessed it, 0.14. And so that is the proportion of people who answered 3 or below. So 3 becomes the 14th percentile, because 14% of the folks are at 3 or below. Similarly, 7 is the 58th percentile. Anyone who chose 7 would know that 58% of the folks are at 7 or below, right? And how did we figure this out? How could we figure it out? We'd go back to this slide and see 29 people chose either 1, 2, 3, 4, 5, 6, or 7. And what is 29 divided by the total number of people? Because there are 50 people. I'm guessing. I'm not guessing, I know. 29 divided by 50 is, you guessed it, 0.58. So we know that 7 is at the 58th percentile because 58% of the folks chose 7 or below. So if you chose 7, you know that you are in you are above or at 58 better, or have more Brahma love in this case, 58% of the folks. Make sense? I certainly hope so. It's how you can identify percentile ranks. Now, this would be the frequency table for that police officer reaction time data. Oh my gosh. Can we quickly notice a pattern here? Well, no, not really. Because look, almost every single officer, almost every single officer has their own unique reaction times. It's difficult to tell if people are clustering anywhere. You're not quickly and easily visually summarizing your data. This is just not going to be anywhere near as useful at identifying the things that you care about, right? So instead of using, when you have continuous data, like reaction times would be, reaction times are an example of a continuous quantitative variable. If you have continuous data, you're going to want to use something else. And that something else is a histogram. That something else is a histogram. So this is a histogram. And so let's sort of walk through the mechanics of a histogram. What a histogram does is it creates a number line along what's called the x-axis. Now, hopefully, you had good quality math instructions, and you know that down here is the x-axis. An axis is a fancy word for a line on a plane. And this is the y-axis. So you've got the horizontal axis, which is the x-axis, and the vertical axis, which is the y-axis. And you're keeping track of things along both axes. And along the x-axis, you create a number line that represents your range of scores. Now, a number line always has smaller numbers on the left and larger numbers on the right. Without exception, that is how number lines are structured. If you have negative numbers, you still have smaller numbers, meaning farther away from 0, right? So -5 is less than -4, right? You end up with negative numbers getting bigger and bigger and bigger in terms of absolute value as you head to the left, and positive numbers, because those are bigger numbers, getting bigger and bigger and bigger in terms of absolute value on the right. Hopefully you know what a number line is. Let me just quickly try to refresh your memory in case you had poor quality math instruction, right? So down here is the number line, right? Notice how 2.5 is bigger than 1.25. And if I kept drawing this number line, eventually I'd get to 0, right? And then if I kept going, I would have -1 and down and down and down and down and down, right? Hopefully you understand the idea of a basic number line. That is my fervent hope, right? This is a number line that's centered at 0. You would have +1 here, +2 here. This stylus is not working for me. You would have then +1 here, positive 2 here. And if you went on the other side of 0, you would have negative 1 here, negative 2 here. That is the standard number line. And what a histogram does, a histogram starts with a number line along the x-axis that corresponds to the range of your quantitative variable, whatever it is. Now, our quantitative variable of reaction times ranged, I think, from 1.21 all the way up to like 2.6 seconds. And so down here on our number line, it ranges all the way over here from 1.21 all the way up to 2.6. And then what you do is you group your reaction times by similar values. And you call this, and then you decide on what your range will be for each of your groupings. And that range will be what's called the bin width. Because you can think of these rectangular bars here as bins, where you're putting like scores together. So for example, here in this center rectangle, or this center bin, this is the range of 1.81 to 1.94. And then over here along the y-axis, you keep track of how many people ended up in a particular range. So here we have 23 people had a reaction time between 1.81 seconds and 1.94 seconds. 23 people fell into the range of 1.81 to 1.94. And so that is a range of, let's see if I can eyeball that range. That is a range of, looks like 0.13 seconds, right? And so then each one of these bins would have a range of 0.13 seconds. All of your ranges have to be the same for all of your rectangular bars that we call bins. What you can then see here on this distribution is that each one of these bins is the same width wide in terms of seconds, right? But 0.13 seconds. And so this is going to be 1.21 all the way to 1.3 something. This is going to be 1.3 something to just over that. Each bin is going to be the same range, right? Same range wide. And what you notice is that most of the people were sort of in the middle. And as you got farther and farther away from sort of the middle reaction time, really, really slow people were not very common. Really, really fast people were not very common. Because look, only 4 people were in this lower range. And only 1 or 2 people were in this upper range. Because over here along the y-axis is how frequently a score occurred. Right? So you're always having to keep track of 2 different things. On any visual representation, like a histogram, you have to keep track of 2 things. You have a number line along the bottom, keeping track of the actual scores, but then along the top, you're keeping track of how many people ended up in a particular range of those quantitative scores. And that range is called the bin width. So, which range is the most common? 1.81 to 1.94. And as you get slower and slower and slower, fewer people are that slow. And as you get faster and faster and faster and faster, fewer people are that fast. And this shape of this distribution is actually called a normal distribution. When most people are in the center of your range, and as you move away from that center point, people are less probable because there are fewer people in those ranges. This is called a density plot. And a density plot is very, very, very similar to a histogram. Along the x-axis, you still have that number line that represents your range on your quantitative variable. So let's say I want to know and I made this this graph here using 100 random numbers that I told a computer algorithm to be normally distributed, right? But let's pretend that this is a variable on how much people love beets. On a scale of -5, which means you hate them, you never, ever, ever want to eat a beet. They taste so bad, you don't understand how anybody ever eats beets, all the way to +5, which would indicate that, like, you have posters of beets on your wall. And, like, you are so in love with this root vegetable that you want to compose sonatas to the wonder that is a beet. With, 0 being in the middle, which is not really a whole lot of strong feelings about that particular vegetable, the beet. And so it's along the x-axis, you still have the actual possible scores. But instead of grouping people in bins and then putting how the actual frequency that each score occurred along the y-axis, instead you put how probable the various scores are. And another word for probability is density. How probable, how much stuff is there, right? And so instead of having actual whole numbers along the y-axis, instead you put the proportions along the y-axis, or the probability along the y-axis. And so another name for a density plot is often called a probability density plot or a probability density function. Because here you can see that a score of 0 is super probable compared to a score of -5. In fact, a score of -5 right here is it's almost a 0 probability. So few people chose -5, a burning hate for beets. It's essentially a 0 probability that someone is going to choose -5. And it's the same thing with +5. So few people chose 5 that the probability someone chose 5 is super low. But a ton of people chose 0, and so this is a super probable score. +1 is a little less probable than 0. +2 is a little less probable than 1, and so on, and so on, and so on. And we say that the entire amount of stuff here is how dense it is. 0 is a very dense or highly probable value. +3 is not very dense. This is not very thick here. Density, you can think about it as like thickness, right? If I have a dense skull, I've got a thick skull. 3 is not very dense, so the score of 3 is not very probable, right? And I can interpret it this way, right? -1 is more probable than -4. Yeah, not probable at all, right? 0 is the most probable of all. And the way a density plot is created is actually you start with a histogram. You start with a histogram, and then you convert the frequencies into proportions or probabilities, and then you smooth out the histogram, where you essentially assume an infinite number of possible cases. Now we're into infinity. We're in infinity land now. Yeah, but it's theoretical at this point. You go, okay, I actually only had 50 people maybe, but let's assume I had an infinite number of people, all with the same essentially the same probability. Let's smooth out the histogram, right? So I can figure out how probable 2.5 is, even though I didn't allow people to say 2.5. I can figure out how probable 1.5 is, even though I didn't actually let people choose 1.5. That's the idea behind a histogram, or a probability density function. You figure out all the different probabilities for all your various outcomes, where everything under the curve, right, would be a probability of 1. What's the probability of answering anything? This entire area under here has a probability of 1. A density plot is also nice because you can actually figure out the probability of ranges of scores, right? I could figure out the probability of having a score from 0 to +5, and that would be essentially half the curve, right? So half the people chose 0 or above. And then I would notice that half the people chose 0 or below. So you can figure out the probability of being in a particular range. Not just the frequency, how many people were in a particular range, but also the probability of being in a particular range. And so density plots are very useful as well. And so the last topic I want to cover today is the idea that there are some very typical shapes of these distributions. And I mean just that, like shapes, like squares and circles and hats, the shape of the distribution. And we're only going to be interpreting histograms and density plots for shape, because they're the ones that are really like a picture, right? And using histograms and density plots, you can identify patterns of distributions where you answer the question, where are the people? Where are the people? And we're going to cover uniform distributions, bimodal distributions, normal distributions, and skewed distributions. And what I have here for you are some formal definitions, which I'll go over real quickly, but then I'll just show you some pictures, because I think pictures are much more useful when describing the shapes of distributions than defining them. But a uniform distribution is defined as when you're considering all the possible values in your range for your variable, every single value is equally probable. The people are equally and uniformly spread out among all your possible outcomes. A bimodal distribution is when you have two scores along your continuum that are very common, and then as you move away from those two highly probable scores, which are called modes, very probable scores, people become less likely. A normal distribution is when you have one very, very common score, and as you move away from that very, very common score, either above that score or below that score, people become less likely because there are fewer people answering in that fashion. And a skewed distribution is similar to a normal one because there's one very, very common score, and as you move away from that score, people become more likely, but there are more extreme scores on one side. So let's look at pictures, much better. Here is a uniform distribution, roughly uniform. It's not perfect because real data does not look like perfect pictures. But a uniform distribution is where all of the particular outcomes are equally likely. And I have not only the histogram here, where I have the counts or frequencies along the side, along the y-axis, but I also have what would be essentially the density plot on top of it, which would just be a rectangle. Because let's say this is your scores on a 200-point cumulative final, right? And essentially one person, and let's say I have basically one person fell into each of these categories. That's the idea behind a uniform distribution. A uniform distribution is all of the various outcomes are equally likely. Getting a 200 was just as likely as getting a 0, just as likely as getting a 20, etc., etc., etc. A uniform distribution, every single possible value is equally likely. That is the essence of a uniform distribution. And the best example I can give of a uniform distribution actually doesn't come from psychology. It actually comes from probability theory. And it's actually if you roll like a die, a 6-sided die, or any kind of non-weighted die. A die is the singular of dice. So if I roll a dice or a die, getting a 1 is just as likely as getting a 2. Getting a 2 is just as likely as getting a 3. Getting a 4 is just as likely as getting and on and on and on. And so if I rolled that dice and I kept rolling that dice and I kept rolling that dice, and I kept track of how many 1s and I kept track of how many 2s and I kept track of how many 3s, I would eventually create myself a histogram where the number of 1s, 2s, 3s, 4s, 5s, and 6s is all roughly the same. And so you end up with a uniform distribution. So named because each outcome has the same, like a uniform, the same probability as any other outcome. A bimodal distribution looks like this, where you have two, and this is, again, real data, never looks perfect. This is what's called a roughly bimodal distribution. And I've gone, and down here at the bottom, you again, along the x-axis, you have the actual values on the thing you're trying to measure. And this ranges from 1.5 to 5.0. So let's say this is GPA. if for people who take super amazing honors classes in in high school, you can actually end up with a GPA of 5 if you take only honors and advanced placement classes, where you get extra GPA points for people with who are very motivated for academic success and lots of opportunities and enrichment. And so here, let's say I have along the x-axis my actual scores, GPA ranging from 1.5, so not so great, all the way to 5.0, perfect, amazing, the most amazing GPA ever. And then along here, I've actually put the proportion or the density, right? Again, I'm not only having the histogram here, how frequently the score occurred, but I'm also putting the density. I'm also putting the density plot here. So on this side, I'm tracking the probability as well. And so what I notice is there's sort of two groups of people, two groups of students. I have people who I have 2.0 is a super common GPA, but then over here, 4.5 is a super common GPA. And as you move away from 4.5 up here, either above it or below it, people become less likely, right? A GPA of 4.0 is less likely than a GPA of 4.5. But then when I look over here, a GPA of 2.5 is less likely than a GPA of 2.0. And in psychology, when you're studying people, oftentimes you might end up with a bimodal distribution if you actually have two groups of people and you don't realize you have two groups of people. And so I might end up with data like this if I decide to sort of track average GPA, high school GPA here at Pierce. I say, I wonder what people's GPAs were in high school. And so I decide to head over to the Center for Academic Success, and I start asking people, hey, what was your high school GPA? What was your high school GPA? And I don't realize it, but what I actually have, I've stumbled on a day when they've brought in really advanced tutors who are taking AP classes, who are working with students who are struggling, really struggling in school and high school. Like it's a high school prep day over in the Center for Academic Success, where you have high school students who are doing awesome working with high school students who are doing terribly. And I don't realize it, but I have the tutors and the tutees all mixed together, and I end up with this bimodal distribution, where you have two scores that are super probable, and then as you move either above or below those super probable scores, people become less likely. This is a normal distribution. Another name for a normal distribution is a bell-shaped curve, because it kind of looks like a bell. Yet another name for a normal distribution is called the Gaussian distribution, so named for Frederick Gauss, G-A-U-S-S, so named for Frederick Gauss. And he was actually a mathematician who was actually able to figure out the mathematical function that defines the normal distribution. Now, you may remember from math class what a function is. For example, there's a line function where if you plug in an x, it's going to spit out a y, and if you plug in another x, it'll spit out another y. And if you plug in another x, it'll spit out another y, and you'll always have this beautiful straight line. It's called the line function. There's a parabola function, squared functions, where you plug in an x and it spits out a y, and you end up drawing this picture that looks kind of like a u or an inverted u. That's called the parabola function. There are sine wave functions for the more advanced mathematicians or physicists among you. The normal distribution is actually an example of a function that if I plugged in an x, I could actually spit out a y, and eventually I would draw this pretty curve. So that is why it's called the Gaussian distribution. Frederick Gauss figured out the actual mathematical equation that would draw this picture. And then this other crazy thing is true. In nature, and particularly with people, our outcomes on variables are usually, or not usually, are often normally distributed. Reaction times are normally distributed. Height is normally distributed. Weight is normally distributed. IQ, intelligence is normally distributed. so many psychological variables as well as physical variables are normally distributed, where there's one sort of center score that is super common, and as you get really, really extreme above it, people become less likely, and as you get really, really extreme below it, people become less likely. So let's use the example of IQ. IQ is a psychological construct. It's measured with standardized IQ tests, and it's outside the purview of this class to sort of discuss whether or not IQ is a good thing to measure, right? Suffice it to say that IQ is something that they do measure, and it tends to be very reliable in its measurement, and it tends to show some validity, at least in some interpretations for some uses. Now, and IQ is absolutely normally distributed. It has an average of 100, and as you get above average to an IQ of 120, an IQ of 100, an IQ of 120, an IQ of 140, all the way to an IQ of 160, people become less probable. There are way fewer people with IQs of 160 than there are people with IQs of 100. So having an IQ of 160 is less probable than an IQ of 100. And as you move the other way, that is also true in the same pattern. Having an IQ of 60 is way less likely than having an IQ of 100. IQ of 40 is even less likely than having an IQ of 60. So as you move above the average or the center point, or below the average or the center point, people become less probable. And because there are fewer people out there, fewer people scoring in those ranges. And that is our definition of the normal or Gaussian distribution. And so the last very common shape of distributions I want to go over is something called skew. And what skew is best understood as an asymmetrical deviation from normality. Start with something that's roughly normal, with one very common score, one what we call peak, right? Now let's go back and look at that. Let's go back and look at a normal distribution, because there's a couple of vocab words I want to share with you first about a normal distribution. And let me just erase some of these scrabbles we have here, right? Right? So when you look at a normal distribution, it has what's called a peak, right? This, and I like to think of it also like a mountain. A normal distribution is often like a mountain. And this is the peak of the mountain. It's the most common or probable score. And these are the tails of a distribution, right? Because they sort of kind of look like tails, right? They're long and thin like a tail. And so this is the peak of the distribution, and these are the tails of the distribution. And it is a symmetrical distribution. That means the left side of the distribution looks the same as the right side of the distribution. And if I drew a line down the center of the distribution, everything on the left and everything on the right is the same. If I folded it in half, roughly symmetrical. And skew then basically says, start out with something that has one peak, one very common value, and make it asymmetrical, but only on one side. And this is another very common way for people's scores to be distributed. And you can actually calculate the extent to which a distribution is asymmetrical, the extent to which it is skewed. We're not going to do it that way. Rather, we're going to talk about skew just as the general shape of distributions. And we say that a distribution is skewed if it's got one peak, but then there are more extreme scores only on one side. And the side where there are more extreme scores, more scores far away from the peak, we say that it is skewed in that direction, because then the average is going to get pulled in the direction of that skew. And so let's look at a picture. So what causes skew? Skew is caused by outliers being on only one side. So what is an outlier? An outlier is a score that is sort of far away from the rest of the group. So if you think about the peak of a normal distribution, that's where all the people are. All the people are clustering at that peak. That's the score where most people are. And in skew, there are more extreme scores only on one side. And so we call these scores outliers because they're out there where nobody else is. They're unusual because there is not a corresponding extreme score on the other side of a similar magnitude. So again, let's look at a picture. Here is an example of skew distributions. Here, we have positive skew. And why is it positive skew? Well, because if you look at the number line down here, you'll notice that there's a peak here, a very common score here, right? And that as you move away from that very common score, there are a whole lot more extreme people on the positive side of this number line. Right? And this is actually very counterintuitive because a lot of students, when they look at this distribution, they're like, well, wait a minute, all the people are in the negative range here. Why would you call this positive skew? Because what skew is a deviation from normality. Skew is where there are more extreme scores. Here, you have something that might be roughly normal, except you have all these weird people over here in the positive direction and no weird people in the negative direction. So it's positive skew because when you look at the average is going to get pulled in the direction of these extreme scores. Kind of like when somebody throws off the curve in an exam. If there are more people, right? If most of the people do sort of crappy, but then there are like lots and lots of people, not lots and lots, but if there are only people who did super awesome without corresponding people who did even worse than the bulk of the people, we call it positive skew. And so you can remember it in one of two ways. I like to remember it as the idea that skew is deviation from normality. Start with the roughly normal and look for the extra extreme scores. Where there are extra extreme scores, like we have here, that is why it is positive skew. You can also think about it this way. It's positive skew because the tail of the distribution points to the direction of the skew. This is positive skew because here is where there are extra extreme scores where there aren't over here. No extra extreme scores in the negative direction. This, on the other hand, on the bottom here is negative skew because most of the people are here in the positive direction. And when you have these extra extreme scores on the negative side of the number line. And again, it's counterintuitive. Most of the people are in the positive range. Why do we call this negative skew? Well, because there are extra extreme scores in the negative direction, pulling any average towards themselves, right? Start with something roughly normal, and then add extra scores, extra extreme weird scores only to one side, and so we call that negative skew. And one last thing I'd like to point out. Anytime, okay, this is called positive skew. It is also called right-hand skew because there's extra extreme scores on the right side. And anytime you have extra extreme scores on the right side, you call it positive skew. Even if, let's say, there are only negative numbers. Because let's say the numbers looked like this. Negative 1,000. And then here, let's say you had negative 500. This would still be positive skew because eventually, moving this direction, you would end up with the positive numbers. Same thing down here. This is not only called negative skew, It's also called left-hand skew because the negative numbers are on the left-hand side of the distribution. And anytime you have extra extreme scores on the left side, you call it negative skew. That's true even if you only have positive numbers. Because let's say down here, you only had positive numbers. It would still be negative skew because eventually negative numbers would be where on the same side as where the extra scores are. And I know it's very counterintuitive, but just remember, we talk about skew as deviation from normality. Start with something roughly normal, and then add extreme scores only to one side, where you're essentially making one tail a whole lot longer than the other. With positive skew, it is the positive direction of the number line that has the longer tail. And because the tail is longer in the positive direction, we call it positive or right-hand skew. On the bottom here, because the tail is so much longer in the negative direction, we're going to call it negative skew, right? Because any average is going to get pulled toward those extra extreme scores on only the left side, right? So skew is understood as where are the extra extreme scores. Where those extra extreme scores are, that is the direction of the skew, because any average is going to get skewed in that direction. And that's all I have for you today. Thank you so much, and I will see you next time when we talk about central tendency and variability.